The outer solar system should be flat. Not perfectly flat. Nothing in nature is, but close enough that for decades we treated it as a solved problem. The 8 planets orbit on a plane tilted less than 2 degrees from the Sun's own equator. The debris field beyond Neptune, the ancient rocks and ice that have drifted out there since the solar system was young, follows roughly the same sheet. Gravity does that. Time does that. 4.5 billion years of orbital mechanics smoothing everything down to a disk, the way water finds level. So when astronomers started mapping the precise orbits of trans-Neptunian objects, the small cold bodies living beyond Neptune, they expected to find that disk. What they found instead was a warp. The orbital plane of the outer solar system is tilted, not by a fraction of a degree, by 15 degrees. The entire disk is bent, like a vinyl record left in the sun, and it has no business being that way. 15 degrees is not a rounding error. It is not instrument noise. It is not the accumulated wobble of a few misclassified rocks. When you measure enough objects across enough of the sky, and you keep getting orbits that cluster around a plane 15 degrees off from where it should be, that is a signal. And signals in orbital mechanics mean one thing: something is pulling. The question is what? The forces we already know about: the Sun, the 8 planets, the gravitational drag of the galactic tide, do not produce a warp like this. Run the models forward and backward with everything in the catalog, and you cannot get 15 degrees. The math comes up short. Whatever is bending the outer solar system's plane is either not in the catalog, or it is something we have never directly seen. This is where the story gets strange in a very specific way. We have been here before, not with this exact anomaly, but with this exact type of anomaly. Orbital tilts and clustering patterns that models cannot explain are how Neptune was predicted decades before anyone pointed a telescope at the right patch of sky. The planet was inferred from the misbehavior of Uranus. The math came first. The discovery followed. That precedent matters here, because the team that found this warp did not find it by accident. They went looking for what could cause it. A research group at Princeton ran the numbers on what kind of object, at what distance, on what kind of orbit, could account for a 15-degree tilt across the outer solar system's disk. They weren't guessing. They were solving an inverse problem, working backward from the observed warp to the mass and position of its most probable cause. And what came out of that calculation was something that should not still be undiscovered in the year we're living in. A planet. A rocky, terrestrial planet sitting somewhere between 80 and 200 astronomical units from the Sun. Closer than you'd expect for something we've never seen. Massive enough to bend an entire orbital plane, and completely invisible to every survey we've run so far. They're calling it Planet Y. Planet Y. The name is deliberately provisional, a placeholder, not a christening. But the object behind it, if it exists, is anything but provisional. It is, according to the Princeton team's best reconstruction, a rocky world. Not a gas giant drifting in the dark. Not an ice planet like Uranus or Neptune. A terrestrial body, the same category as Mercury, Venus, Earth, Mars. Sitting at a distance so extreme, it makes those planets look like they're practically inside the Sun. The mass estimate runs between roughly half of Mercury's mass on the low end and something close to Earth's mass on the high end. That is a wide range, and the researchers are honest about it. But even the lower bound is not small. Half a Mercury, at 80 astronomical units, is still gravitationally significant, enough to nudge over millions of years the orbital geometry of everything around it. 80 to 200 AU. To put that in terms a human brain can actually hold, Earth sits 1 AU from the Sun. Neptune, the outermost planet we formally recognize, sits about 30. 80 AU is nearly 3 times beyond Neptune. 200 AU is more than 6 times beyond Neptune, pushing into a region so remote that sunlight takes over 25 hours just to arrive. The Sun from that distance is not a star you'd warm yourself under. It's a bright point, the brightest point in the sky, but still just a point. And Planet Y isn't inferred from a direct detection. Nobody caught it in a telescope frame, measured its reflected light, tracked its motion across the sky over successive nights. What the Princeton team found is a gravitational fingerprint, the shape of the disturbance the object leaves behind in the orbits of the bodies around it. They looked at the warp and asked, what precisely would have to be out there to produce exactly this signature? The answer converged on a single class of object, rocky, terrestrial, somewhere in that 80 to 200 AU band. This is the inference method that has worked before. It worked for Neptune. It worked, arguably, for the prediction of general relativistic corrections to Mercury's own orbit. You don't always need to see the thing to know it's there. Sometimes the distortions it leaves in the fabric around it are proof enough. Provisional proof, but proof with a number attached. What makes Planet Y unusual, beyond its existence, is its category. We have never found a planet like this in the outer solar system. The outer solar system is supposed to be the domain of gas and ice. The Jovians, the Neptunians, the icy dwarfs. Rocky worlds are supposed to belong close in, where the early sun's heat drove away lighter materials and left dense silicates behind. A terrestrial body at 80 plus AU breaks that rule badly enough that it demands an explanation. And the explanation, whichever one turns out to be correct, changes how we understand where we came from. So how do you actually find a planet you cannot see? The Princeton team's answer starts not with telescopes, but with a database. The positions, velocities, and orbital elements of hundreds of trans-Neptunian objects, the icy bodies orbiting beyond Neptune that have been cataloged over decades of sky surveys. These are the witnesses. Planet Y is the suspect. The method is reading the witness's testimony and asking, does any single hidden body explain why they're all leaning the same direction? The specific signal the researchers measured is that 15-degree warp, the systematic tilt of the outer solar system's orbital plane relative to the ecliptic, the plane defined by the inner planets. That tilt isn't random scatter. Random scatter looks like noise. It cancels out across enough objects. What the team found is a coherent directional bias, a population of bodies whose orbital inclinations cluster in a way that points toward a common gravitational cause. That clustering is the fingerprint. The modeling works in two stages. First, statistical. Take the observed orbital distribution of the trans-Neptunian population and ask whether the clustering could plausibly arise by chance. The answer in their analysis is no. The signal is strong enough that a coincidental arrangement is unlikely enough to take seriously. But statistical significance alone doesn't tell you what the cause is. That's where the second stage comes in. Dynamical simulation. In the dynamical models, the team essentially runs the solar system forward and backward in time with a test object inserted, varying its mass, its orbital distance, its inclination, its period, and asks which combinations of those parameters reproduce the observed warp. The space of possible solutions narrows fast. A gas giant at that distance would produce a different signature. A very distant object would produce a weaker one. The sweet spot, the region of parameter space where the simulated solar system matches the real one, points consistently towards something roughly Mercury to Earth in mass, orbiting somewhere between 80 and 200 AU. Planet Y. Now, the uncertainty. 80 to 200 AU is a wide range. That's not a precise orbit, it's a confidence interval, and a broad one. The mass estimate carries similar fuzziness, and the trans-Neptunian object catalog itself is incomplete. Surveys have preferential coverage of certain patches of sky, which can introduce biases that look like real clustering. The Princeton team worked to account for those selection effects, but accounting for a bias and eliminating it are different things. Independent researchers are already stress testing the dataset to see whether the signal survives stricter cuts. What keeps the result compelling despite those caveats is the internal consistency. Different subsets of the trans-Neptunian population, analyzed separately, point toward the same general region of parameter space. The signal doesn't fall apart when you probe it. It reproduces. That's not a guarantee of a planet. It's a reason to keep looking. The math has drawn a circle on the sky and said, somewhere in here. Now the question is whether any instrument alive today is capable of finding whatever is inside it. That circle on the sky is not where Planet 9 lives. And that distinction matters more than it might sound. Planet 9 has been a live hypothesis since 2016, when Caltech astronomers Mike Brown and Konstantin Batygin noticed a different clustering in a different set of trans-Neptunian objects. Elongated orbits, all tilted and pointed in roughly the same direction, as if something enormous had shepherded them into alignment over billions of years. Their candidate is a giant, somewhere between 5 and 10 Earth masses, possibly larger. A world closer in character to Neptune than to anything with a rocky surface. And it sits far deeper in the outer solar system. Estimates range from 400 to 800 AU out at, maybe more. You would not find Planet 9 by looking where the Princeton team is looking for Planet Y. They are not the same object. The orbital geometry is different. The mass is different. The inferred distance is different. Planet 9, if it exists, is a gas-dominated world on a highly elongated path that swings it to enormous distances and back. Planet Y is modeled as rocky, Mercury to Earth in mass, so perhaps a tenth of Planet 9's bulk, and it orbits at 80 to 200 AU, which is practically nearby by comparison. Close enough, in principle, that the next generation of surveys might actually image it directly. Planet 9's proposed orbit would keep it so faint and so far that even Rubin may struggle to pin it down within the survey window. Here is the sharper point. The outer solar system appears to be producing multiple anomalies that cannot all be explained by the same object. The clustering brown and Batygin identified and the orbital warp the Princeton team modeled are not obviously the same signal. They involve different populations of objects, different dynamical signatures, different implied masses and distances. One planet cannot easily account for both unless its orbit is precisely tuned in ways that strain credibility. The more parsimonious reading is that there are two separate gravitational sources out there, which would mean two undiscovered worlds, not one. That is a remarkable thing to sit with. Astronomers spent years arguing about whether a single hidden planet could explain a single anomaly. Now the data may be pointing at two. Neither confirmed, neither ruled out, both inferred entirely from the way they bend the paths of smaller things they have never directly touched. The solar system we thought we knew, 8 planets, a handful of dwarf worlds, a belt of ice, may have been an incomplete picture all along. Planet Y and Planet 9 are not rivals. They are, if the math holds, two different holes in our map. Two holes in the map. And immediately the next question presses in, not just whether these objects exist, but where they came from. Because a planet sitting 80 to 200 astronomical units from the Sun is not simply a planet that formed there and stayed put. That distance is a problem. The solar nebula, the disk of gas and dust our solar system condensed from, was too thin and too spread out at those distances to build a planet from scratch in any reasonable time frame. The raw material was there, barely, but the collisions needed to aggregate it into something the size of Earth were too infrequent, the orbital periods too long. Planet Y, if it is real, did not simply grow where it sits. It got there somehow. There are two scenarios on the table, and they point in genuinely different directions about what our early solar system was like. The first is that Planet Y is a homegrown object, rocky, formed in the inner solar system or just beyond it, somewhere between 1 and 10 astronomical units out, where planet formation was efficient and material was plentiful. It built itself up over millions of years, grew to something approaching Earth's mass, and then got thrown. A gravitational encounter with a giant planet, Jupiter, most likely, or a young Saturn, could have done it. The early solar system was a demolition derby. Jupiter alone is thought to have scattered hundreds of planetesimals outward during the first few 100 million years, and some of those encounters were violent enough to fling objects onto enormous, highly elliptical orbits. A body massive enough could have been pushed outward to extreme distances while retaining just enough interaction with the Sun's gravity to stay bound. Barely, on a long, stretched orbit that keeps it hundreds of AU out for most of its cycle. This scenario is uncomfortable in a productive way because it means we may have lost a planet. Not lost in the sense that it was destroyed. Lost in the sense that it was always there. Formed in the same neighborhood as Earth. And then the giant planets reshuffled the deck violently enough that it ended up in the dark at the edge of the system. The solar system we see today, orderly, stable, 8 planets in tidy orbits, is the result of that chaos settling down. But some of what got flung outward never came back. The second scenario is stranger. Planet Y is not native at all. It formed around a different star entirely. A rogue planet, ejected from its birth system and wandering through interstellar space, and our solar system captured it. The Sun, in the early days, was part of a dense stellar nursery, a cluster of young stars packed close enough that gravitational interactions between systems were not rare. A planet passing through at the right speed, at the right angle during one of those close stellar approaches, could have been slowed by the combined gravity of the Sun and the giant planets enough to fall into a bound orbit. Not a perfectly circular, well-behaved orbit, a wild one. A long, elliptical path far from the Sun, where it has been circling ever since. The orbital geometry of planet Y, if the Princeton modeling is right, does not cleanly distinguish between these two options yet. Both could produce something in the 80 to 200 AU range. Both could produce the tilt signature the team detected. What would distinguish them is the orbit's exact shape, its inclination relative to the plane of the solar system, and possibly its composition. A captured rogue might carry a different chemical signature than something that condensed from our own nebula. Those details require actually finding the thing. But the question of which scenario is true matters enormously, because each one describes a different early solar system, one where our own formation process was messier than we assumed, and one where we are carrying a piece of someone else's solar system. That phrase deserves to sit for a moment, because it is not metaphor. It is a literal description of what capture would mean. Rogue planets are not exotic or rare. Current estimates suggest there may be more free-floating planets in the Milky Way than there are stars. Most of them were born the normal way, inside a protoplanetary disk orbiting a young sun, and then ejected. The mechanism is usually the same: gravitational violence between the giant planets of a young system. Jupiter-sized bodies, still settling into their orbits, can scatter smaller planets like billiard balls. Some get nudged inward, some get locked into resonance, and some get flung outward with enough velocity to leave the system entirely, at which point they become permanent wanderers, carrying no star, heated only by their own residual formation warmth slowly bleeding into the cold. Our own solar system almost certainly ejected planets during this period. The leading models of early solar system dynamics, the Nice model and its successors, require a phase of giant planet migration that would have scattered a significant portion of the original planetesimal population into interstellar space. We sent rogues out. The question is whether we ever took one in. Gravitational capture without a third body is essentially impossible. A planet moving through interstellar space on a hyperbolic trajectory has more energy than the Sun's gravity can hold. For capture to happen, something has to bleed that energy away. In the early solar system, that something was the stellar cluster itself, dozens of young stars in a volume of space compact enough that their collective gravity created a temporary well deeper than any single star's. A rogue entering this environment could lose just enough kinetic energy through a close pass near one of those neighboring stars, combined with a gravitational tug from Jupiter or Saturn, to slip from a hyperbolic path into an elongated bound orbit. The window would have been narrow. The geometry would have had to be close to perfect. But the cluster gave the solar system millions of years to run that lottery, and the odds were not as long as they would be today. What makes this harder to dismiss is that capture events have left traces elsewhere in the solar system. The leading theory for the origin of Triton, Neptune's largest moon, is that it was a captured Kuiper Belt object, or possibly something from even farther out, snagged by Neptune during the same chaotic period. If Neptune could capture a moon, the Sun, with orders of magnitude more gravity and the help of a dense stellar neighborhood, could plausibly have captured a planet. The early solar system was not the ordered, placid place we sometimes picture. It was a construction site. Giant planets migrating inward and outward, planetesimals being flung in every direction, and neighboring stars close enough to matter. Planet Y, if it is real and if it is captured, would be a relic of that chaos, a frozen record of a collision that never happened, a near miss between solar systems 4 billion years ago that left something behind, a frozen relic of the early solar system, flung to the edges or captured from outside. Either way, it should still be out there. So why haven't we found it? The short answer is distance. 80 astronomical units is already a place that makes the word far feel inadequate. At 80 AU, you are 80 times the distance from the Earth to the Sun, past the Kuiper Belt, past Pluto, past almost everything we have ever sent a spacecraft near. At 200 AU, the Sun is a bright star, not a warming presence. Light that left our sun 8 minutes ago takes over 27 hours to reach the outer edge of Planet Y's probable orbit, and distance does something brutal to brightness. Objects in the outer solar system reflect sunlight, and reflected brightness falls off with the fourth power of distance. Pluto at roughly 40 AU is already difficult. An object at 80 AU reflects less than a sixth of the light Pluto would at the same size. Push it to 200 AU and you are looking for something that returns almost no light at all. A dim, slow-moving point that could spend decades crossing a patch of sky smaller than your thumbnail held at arm's length. Speed compounds the problem. The farther out an object orbits, the slower it moves across the sky. At 200 AU, Planet Y would drift so gradually that distinguishing it from a background star in a single observation is nearly impossible. You need to compare images taken months or years apart and look for the thing that moved, which means patient, methodical, wide-field surveys taken on a strict cadence. Those are hard to fund, hard to execute, and hard to sustain. We have tried. The Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, scanned large fractions of the sky and found thousands of Kuiper Belt objects, while coming up empty on anything planet-like beyond them. The Dark Energy Survey, designed primarily for cosmology, turned its wide-field camera on stretches of the outer solar system as a bonus project. Again, objects discovered, nothing planetary scale. The Catalina Sky Survey, originally built to hunt near-Earth asteroids, contributed patches of outer solar system coverage with no confirmed detection. What these surveys share is a limit. They were not built for this. Their sky coverage was partial, their cadence inconsistent for this specific science case, or their sensitivity stopped just short of where a rocky world at extreme distance would sit. Each one expanded the map of the outer solar system substantially. None of them could rule Planet Y out. They simply could not see far enough, faint enough, or systematically enough to close the question. The signal in the orbital data says something is there. The telescopes we have built so far lack the combination of depth, coverage, and patience to confirm it. That mismatch has held for years. It is about to change. The instrument that changes this sits in the Chilean Andes, on a ridge called Cerro Pachón, at an elevation where the air is thin enough and dry enough that the sky above it is almost surgically clear. It is called the Vera C. Rubin Observatory, and it was not built in response to Planet Y. The planning began decades ago, but it is, almost by accident, exactly what this search requires. The core of Rubin is a camera, not a camera in any ordinary sense. An 8.4-meter primary mirror feeding a 3 billion pixel focal plane, the largest digital camera ever built for astronomy. A single image it captures covers an area of sky roughly 40 times the size of the full moon. That field of view is not just impressive, it is the whole point. The survey Rubin is running is called the Legacy Survey of Space and Time, LSST. Over 10 years, it will photograph the entire visible southern sky repeatedly, systematically, on a cadence designed to catch things that move or change. Every patch of sky it can reach will be revisited roughly every 3 to 4 nights. That rhythm is what matters. Finding a slow-moving object at 80 to 200 astronomical units is not about a single deep image. It is about watching the same patch of sky over months and years and watching something drift, almost imperceptibly, against the fixed stars behind it. A rocky world at 150 astronomical units moves across the sky at something like 1 to 2 arcseconds per hour. That is roughly the apparent width of a human hair held at arm's length per hour of motion. Individual images cannot distinguish it from a faint background star. But stack exposures taken nights apart, compare them carefully, and that motion becomes a fingerprint. Rubin's software pipeline is built to hunt exactly that fingerprint, automatically, across billions of detected objects, night after night. The sensitivity matters just as much as the cadence. Rubin will reach down to objects around 27th magnitude. That is nearly 400 times fainter than what the Sloan Digital Sky Survey could detect for moving objects, and significantly deeper than most targeted outer solar system searches. A rocky body at the mass and distance range Planet Y is predicted to occupy would sit comfortably within Rubin's reach, provided it reflects enough sunlight. That is the one remaining physical unknown, the surface albedo. A very dark, absorptive surface would push it toward Rubin's detection floor, A brighter one, more reflective ice or silicate rock, would make it straightforward. The 10-year window is not arbitrary. That is how long the full LSST baseline runs. Within that span, any Planet Y candidate would need to appear in multiple independent observations, move consistently with a predicted orbit, and survive the kind of scrutiny that rules out artifacts and background noise. Confirmation is not a single moment. It is an accumulation of detections that converge on something real. First light for Rubin's science operations came in 2025. The clock is running. The outer solar system that has deflected every previous instrument, too dark, too vast, too poorly mapped, is now, for the first time, inside the reach of something built to finish the question. So assume it happens. Assume Rubin finds it. Multiple detections, consistent orbit, the signal hardening into something that cannot be explained away. What exactly changes? Start with the immediate, concrete consequence. The solar system gains a planet. Not a reclassification, not a demotion, not a redefinition of what counts. A new world, physically present, that was here the entire time we thought we had the full inventory. But more specifically, it gains a planet in a category that does not currently exist out there. We have the terrestrial four, Mercury, Venus, Earth, Mars, packed inside the first couple AU. Then the gas and ice giants from 5 AU out to 30. Planet Y, if real, would be a rocky body sitting at 80 to 200 AU, tens of billions of kilometers beyond Neptune. There is nothing like that in the current catalog. It would be its own thing, stranded in the cold dark at the edge of the system, a class of one. That forces a harder question. If the solar system can produce or capture a rocky world that ends up there, why only one? Formation models do not comfortably accommodate this outcome as a rare exception. If the conditions existed for Planet Y, they may have existed for others. The confirmed detection would not close the question of the outer solar system. It would open it wider. The rewrite for formation models runs deep. The standard picture of how the solar system assembled, accretion, the late heavy bombardment, the Nice model's orbital reshuffling, already strains to explain the architecture we see. Planet Y arriving via capture would mean our early solar system was embedded in an environment dense enough to snag a free-floating world, which puts real constraints on the stellar nursery the Sun formed in. If it formed in place and was flung outward, something had to do the flinging. A giant planet encounter violent enough to send a rocky body to those distances without ejecting it entirely. Neither version is tidy. Then there is the quieter, harder to quantify shift. Since 1930, the known boundary of the solar system has been essentially fixed. We added detail, Kuiper belt objects, scattered disk bodies, the Oort cloud inferred but not seen, but no new full-scale planet. The assumption that we had mapped our own neighborhood, that the major inventory was done, became background noise. Confirmation would break that assumption permanently. It would mean that a world potentially rivaling Earth in mass has been orbiting the Sun, unseen, for billions of years, not in some distant galaxy, not in another star system. Here, in the same gravitational family as the planet you are standing on right now. That is the philosophical weight underneath the orbital mechanics. Not that the universe is strange, we already knew that, but that the strangeness is this close, that the solar system we thought we understood still has a room we have never entered, and that room may not stay locked much longer. Vera C. Rubin Observatory is already imaging the sky. Its first data releases are beginning to land. Over the next decade, its LSST survey will cover the southern sky repeatedly, building a time-lapse of the outer solar system that no instrument before it has been able to produce. If Planet Y is real, if a rocky world is out there at 80 to 200 astronomical units, tilting orbital planes and leaving its fingerprint on the paths of smaller bodies, Rubin has a genuine shot at finding it. Not because finding things at that distance is easy, but because Rubin was built at exactly the scale where easy stops and necessary begins. What we are watching right now is science operating at its actual edge, not the polished edge of a textbook, where the answers are already known and the only question is whether you have memorized them. The raw edge, where the signal is real but the object is not confirmed, where the math is compelling but the sky is not yet agreed, where a team of researchers at Princeton have done everything right and are still waiting, like everyone else, for the light. That uncertainty is not a failure. It is what the process looks like from the inside. The 15-degree warp in the orbital plane is not going away. The statistical argument that something massive caused it has not been dismantled. What the field lacks is the direct observation that would settle it, and the direct observation is 10 years of survey time away, at most. In planetary science terms, that is nothing. In human terms, it is the length of a career, the stretch of a childhood, the decade between who you are now and who you will be when the answer arrives. There is something quietly strange about sitting with that. We have mapped the large-scale structure of the universe across billions of light-years. We have imaged a black hole's shadow 40 million light-years away. We have sent probes past every planet in the solar system and watched Pluto's heart-shaped plane resolve from a blur into a landscape. And yet there may be a world, rocky, massive, ancient, orbiting the same star as Earth, close enough that its gravity is already bending the paths of its neighbors, and we have simply never seen it. Not because it is impossibly far, because the outer solar system is dark and vast, and we only recently built the instrument capable of looking hard enough. Planet Y may be there, it may not. The warp is real, the explanation is still a candidate. Rubin is counting down, and somewhere between 80 and 200 times the distance from the Earth to the Sun, in a region of space we have never properly surveyed, the answer is already waiting, patient, cold, and entirely indifferent to whether we find it. The solar system did not get stranger when this hypothesis was published. It was always this strange. We are only now asking the right questions with the right tools at the right moment to find out.